Good evening once again. This is SK Ghosh. I would like to welcome all of you to the continuation of our training and capacity building program. This is part of component S9 of the Urban Resilience Project. I'm sure most of you have been attending these seminars for a while. So I don't think any further introduction is necessary. Today it is structural module number 3. The topic, as you see, is gravity load provisions of the 2020 edition of the Bangladesh National Building Code. I had a bit of an announcement, but because most people have not arrived, I probably will start with the seminar and either make the announcement in the middle someplace or at the end. Hopefully, I will not forget by then. The gravity load provisions are in Part 6, Chapter 2. But in Part 6, Chapter 1, the title of the chapter is Definitions and General Requirements. There is a section on design for gravity loads, as you see, 1.4. And in that chapter, the topics covered are, first of all, there is a general section, then floor design, roof design, reduction of live loads, hosting of live loads, restrictions on loading, special considerations, deflection, and camber. Other than the posting of live loads and restrictions on loading, most of the content is repeated in chapter 2. So I am not going to talk about any of these. There is also a section 1.6 on design for miscellaneous loads. Under that, the topics are self-straining forces, stress reversal and fatigue, flood, tidal or storm surge, and tsunami, rain loads, other loads. The stress reversal and fatigue is not talked about in chapter 2. Tsunami loads are also not talked about in chapter 2. And it is not that you have a lot of guidance given in chapter 1 either, but they are mentioned. Kind of similarly, as part of the other loads 1.6.6, these are listed in chapter 1. Temperature effects, soil and hydrostatic pressure, impacts and collisions, explosions, fire, vertical forces on air raid shelters, loads on helicopter landing areas, erection and construction loads, moving loads for crane movements, creep and shrinkage, dynamic loads due to vibrations, construction loads. Where I have a section number given, the particular load is covered in chapter 2, and we will go over the provisions. Where there is no section number, chapter 2 really does not talk about the topic, moving loads for crane movements. You do not have guidance that you can use in chapter 2. Fire obviously is a big part of the code. You have had seminars on the fire safety provisions of the BNBC, but structural design for fire resistance is not covered in chapter 2 either. The most important part, to my mind, of chapter 1 is this section 1.9, design and construction review. This is, strictly speaking, not part of gravity loads. I didn't even have to say strictly speaking. This is not part of gravity loads. But I think this is a very significant part of what BNBC has to tell us up front. And I think it will be worthwhile spending a couple of minutes on the provisions of 1.9, design and construction review. Every building or structure designed shall have its design documents prepared in accordance with 191. So we will look at that section. The minimum requirements for design review and construction observation. Those are very important terms. Design review and construction observation shall be those set forth under sections 192 and 193. So we will look at those as well. So the documents shall have design documents prepared in accordance with 191. Design review shall be in accordance with 192. Construction observation shall be in accordance with 193. So this is 191, design document. Quite an important section in my opinion. The design documents shall be prepared and signed by the engineer responsible for the structural design of any building or structure intended for construction. Signed by the engineer responsible for the structural design. The design documents shall include a design report, material specification, and a set of structural drawings. That the code is very, very clear. You have to have those three things: a design report, material specifications, a set of structural drawings, which shall be prepared in compliance with 192, 193 below for submittal to the concerned authority. For the purpose of this provision, the concerned authority shall be either persons from the government approval agency for the construction, or the owner of the building or the structure, or one of his representatives. The owner part I find a little curious. Typically, it is a governmental authority. In any case, Dhaka metropolitan area, it is RAJUK that you are dealing with. So for purpose of this provision, the concerned authority, meaning RAJUK, shall be RAJUK will be the concerned authority. So it talked about design report, material specifications, and structural drawings. This is the design report part. The design report shall contain the description of the structural design with basic design information as provided below. And there is a long list actually given, which I have not reproduced here. So that this is important. So the design report shall contain description, etc., so that any other structural design engineer will be able to independently verify the design parameters and the member sizes using this basic information. The design report shall include but not be limited to the following. So this is talking about some other structural engineer independently verifying, but a significant use of a design report is in the future when a question arises about a building. Some engineer who had no involvement in the design of the building, if given access to the design report, can figure out the basis of the design. So this is a pretty important document. Structural drawings and material specifications, the other two parts. Drawings shall include but not be limited to the following. There is quite a bit said about structural drawings, which is important, and this is not typical of American codes, for instance, but that way I think it is very good that BNBC gives you very specific guidance. Design review. This I cannot emphasize anymore, and Project S9 is really about design review and inspection, which is not a term used in chapter 1, but I will come to that in a second. But design review is a large part of what Project S9 is about. So the design documents specified in 191, which we just went through, shall be available for review when required by the concerned authority, okay? Which in your case again will be RAJUK. Review shall be accomplished by an independent structural engineer qualified for this task and appointed by the concerned authority. This is interesting that BNBC says this. Independent structural engineer qualified for the task appointed by RAJUK. Design review shall be performed through independent calculations based on the information provided in the design documents prepared and signed by the original structural design engineer to verify the design parameters, including applied loads, methods of analysis and design, and final design dimensions and other details of the structural elements. So this is extremely interesting. Design review shall be performed through independent calculations. So as part of Project S9, we have actually recommended to RAJUK very strongly that third-party reviewers be appointed for not only structural design review, but also for non-structural design review. We have not, however, insisted that design review shall be performed through independent calculations. This is in the BNBC. It is up to RAJUK how much of it they want to enforce. But I find it very interesting that the code has chosen to say this. The reviewing engineer shall also check the sufficiency and appropriateness of the supplied structural drawings for construction. This is also important. Shall also check the sufficiency and appropriateness of the supplied structural drawings for construction. Somebody needs to take a look at that, that the drawings are good enough for the construction purposes. Then the review that the code talks about. Construction review. We talked about design review. This is now construction review. Construction observation. This is the term BNBC has chosen to use. Shall be performed by a responsible person who will be a competent professional appointed by the owner of the building or the structure. Okay? This is everything said here is important. Construction observation shall be performed by a responsible person who will be a competent professional appointed by the owner of the building or the structure. Construction observation shall include but not be limited to the following: specification of an appropriate testing and inspection schedule prepared and signed with date by the responsible person, a review of testing and inspection reports, and a regular site visit to verify the general compliance of the construction work with structural drawings and specifications provided in 193 above. Now, what I think is extremely important is everything that is being talked about is what the owner is required to do. Okay? The term here is observation. Now, a big part of what S9 is dealing with is structural inspection. Structural, also non-structural. Inspection is done by the authority, in your case, RAJUK. That is not, BNBC does not talk much at all about the inspection part. So this observation is important. This is the owner's responsibility, without which things really do not work. But then there has to be independent inspection by the authority, which is RAJUK, and that is not talked about in chapter 1. Okay. With that, we go to the chapter 2, part 6, where loads are specified. Loads on buildings and structures is the title of the chapter. So we in this chapter have not only gravity loads, but also everything else that we have to deal with in structural design. So there are sections on dead loads, live loads, wind loads, earthquake loads, then miscellaneous loads, under which there are quite a few listed, and then uh, what do we do with these loads in structural design? That's where the combinations of loads come in. Very, very important section 2.7. I will in fact start with that, combinations of loads. But let us talk about the loads for a little bit. I want you to think in very broad terms. So when we put up a structure, when an owner spends money acquiring land and building a structure, the sole purpose of the structure, I don't know if you ever thought in these terms, is to carry live loads. Those are the only user-imposed loads. We want to do something on the floors of the structure. We want to sleep on them or work on them or dance on them or whatever we want to do. We want to carry on activities on the floors of the structure, maybe also on the roof. And those activities will impose what we call live loads on the structure. In order to carry those live loads, we have no choice but to also resist the dead loads, which is essentially the weight of the structure, the weight of the materials, everything supported on the structure. So the dead loads, which are also gravity loads acting downwards like live loads, are the first parasitic loads that an engineer has to deal with. We don't put up a structure to carry dead loads, but we have no choice. Those are imposed on us. Wind and earthquake are exactly the same way. Those are environmental loads, as we call them. Those are not user imposed. But as soon as we put up a structure, we are interfering with the free flow of wind. A structure stands in the way of wind. So the wind does things to the structure. It imposes loads. And those have to be dealt with in structural design. This is another major parasitic load that we have no choice but to think about in structural design. Earthquake loads are exactly the same way, parasitic. We do not put up a structure to carry earthquake loads, but we have no choice. If the structure is in earthquake country, we have to spend a lot of time and effort making sure that the structure will be standing up in an earthquake. Okay? So live loads are the purpose of putting up the structure, but then all those other loads are imposed on us. The miscellaneous loads that BNBC specifically addresses are rain loads, loads due to flood and surge. Those we are largely not going to discuss because in the Dhaka metro area, you do not have surge for sure, and flooding, I do not believe, is a major problem. Temperature effects, soil and hydrostatic pressure, loads due to explosions. Quite a bit is said in section 2.6.6, but that is a specialized topic and I would not go into it today. Vertical forces on air raid shelters, obviously very specialized. Loads on helicopter landing areas, helipads. This is also specialized. IBC also has provisions on that, but that's not something I want to discuss because of the specialized nature. And then significantly, there is a section on erection and construction loads, which we will take a look at. So we will start with design load combinations, as I said. We have two sets of design load combinations, ASD or allowable stress design load combinations, And then strength design load combinations. Strength design is also called load and resistance factor design, LRFD. Steel people use that term. I did not see that term used that often, at least in BNBC, but anyway, I did want to mention that. So there is a set of ASD load combinations. There is a set of strength design load combinations. Then there are load combinations for extraordinary events. And then something we do not have in US codes, load combinations for serviceability. So that I found to be interesting and important, load combinations for serviceability. Now, something very, very basic. And I think what I'm going to say next is probably the most important thing I will say during this entire seminar. And please remember what I'm going to say for all time to come. A lot of confusion goes away if you think in terms of what I'm just going to tell you. Okay, load combinations are really not load combinations, as I wrote in the last line. You cannot combine loads. Dead loads act downwards on the structure, live loads work downward on the structure. Wind loads act sideways. How do you combine dead and live loads with wind loads? You cannot, and we never do. We have never tried to combine dead loads with wind loads. That's not what the load combinations do. What we combine through load combinations are the effects of loads. Dead loads cause bending moments, shear forces, axial forces at various critical sections of our structural members. So do live loads, so do wind loads. And those bending moments, shear forces, axial forces can be combined, and we do combine them for design purposes. Okay. So when we talk about structural design, we impose loads on not so much the structure, but an analytical model of our structure. The analytical model has to be proper. And we impose dead loads and figure out what the bending moments, shear forces, axial forces are in the various structural members. This requires structural analysis. We do the same thing with live loads. We impose them on the structure. We find out what the bending moment, shear forces are. Then we independently apply wind loads on our structure, and we figure out the bending moments, shear forces, etc. in the structural members. Then in the design of a structural member, we combine the bending moments caused by dead loads, the bending moments caused by live loads, the bending moments caused by wind loads, and then we design for the resultant bending moments. Okay, so this is the process that you always have to have in the back of your mind. So we are combining the effects of loads, the internal forces caused by the external loads, the bending moments, the shear forces, the axial forces, not the loads themselves. Okay? So that's what we are saying in the next picture as well. Okay. So in the top picture, dead loads are imposed on our structure. You see the bending moment distribution and the shear distribution in the lower picture. Okay. So these are the imposed dead loads. These are the shears on that particular beam. These are the bending moments on that particular beam. This is earthquake load, okay, lateral. Instead of wind, we talk about earthquake in this particular slide. So the earthquake forces cause this shear distribution on the same member and this bending moment distribution on the same member. So through the design load combinations, we combine this shear and that shear. This is one of the load combinations, 90% of the dead load effect plus 100% of the earthquake load effect. And that gives us this resultant shear distribution. Similarly, with the bending moments, 90% of that, 100% of that added together gives us this bending moment distribution. And those are the bending moments and shear forces for which we have to design this beam. Although there are other load combinations also. This is not the only one to consider. Okay? So load combinations are not load combinations. Those are combinations of load effects or combinations of internal forces caused by loads. Okay. These are the ASD, allowable stress design load combinations of BNBC 2020. Before we got started, well, first of all, I should, so this has D, L, F, H, T, and L sub R. I think I will get back to that load combination and I will say what I was about to say. The notation, always important. Notation is in at the beginning of chapter 2. So D is dead loads or related internal moments and forces. Okay, so the notation tells you that we are talking about the internal forces or moments. Dead loads, they proceed to give you definition of dead load as part of the notation. Consists of weight of the member itself, weight of all materials of construction incorporated into the building to be permanently supported by the member, including built-in partitions, weight of permanent equipment. We will look at that definition again when we go to the dead load section. E is the total load effect of earthquake that includes both horizontal and vertical or related internal moments and forces. So E has a horizontal, E consists of two parts, horizontal earthquake effect, vertical earthquake effect. We will talk about that quite a bit next week, but E is the combined effect of earthquake in those load combinations. F is the loads due to weight and pressures of fluids. F is for fluids. These have to be fluids with well-defined densities and controllable maximum heights. So F is the weight or pressure of fluids or related internal moments and forces. F sub A, loads due to flood or tidal surge or related internal moments and forces. So F sub A is for flood loads. H, loads due to weight and pressure of soil. The H is for hydrostatic pressure. And so pressure of soil, water in soil or other materials, related internal moments and forces. L is the live load due to intended use and occupancy, including loads due to movable objects and movable partitions, and loads temporarily supported by the structure during maintenance or related internal moments and forces. Those things are important, including loads due to movable objects and movable partitions. So movable partition load is live load, not dead load. And loads temporarily supported by the structure during maintenance, then or related moments and forces. For resistance to impact, if resistance to impact loads is taken into account in design, such effect shall be included with the live load L. That's also something important that is said. Okay, so resistance to impact has to be included in the live load. L sub R is roof live load. So there was a time, I do not remember when that changed. When I started out, definitely there was no distinction between floor live load and roof live load. It was all L, and also for the roof, we always used L. Then in AC7 at some point, a major distinction was made. So now L is floor live load, L sub R is roof live load. R is rain load. T is very important in certain applications, not always. Self-straining forces, cumulative effect of temperature, creep, shrinkage, differential settlement, shrinkage compensating concrete, combination thereof, etc., etc. T stands for temperature, but I would like you to think of T as the effect of restrained volume changes. Restrained volume changes. Okay, a very simple, crude example. Okay, you cast a 20 feet long concrete beam. As soon as you are done casting it, it begins to shrink. Concrete shrinks because water evaporates out of the concrete. So in time, several months, your 20-foot long beam will be 19 foot 11 inches. Now, if you let the shrinkage take place unimpeded, nobody is going to miss the 1 inch. But that's not the problem. The problem is basically all the time in cast in place concrete, this beam frames into columns or walls, which will not let the beam shrink. The beam wants to shrink, but the walls that the beam frames into won't let it shrink. And when that happens, when you restrain the shrinkage, the beam is set in tension. Something wants to shorten, you don't let it shorten. That means you are pulling on it, you are setting it in tension. And concrete is weak in tension. That's where the problem is. Now this member is going to crack. And you have to worry about it. The cracking cannot get out of hand because that can eventually lead to even failure. Okay, so think of T as the effect of restrained volume change, and also remember that this is extremely important in precast concrete. That's a big thing that engineers of precast concrete also always have to deal with. Precast members are built in the factory, brought to the job site, put together. They're going to shrink even after they're put in place. And if you don't allow for their shrinkage, it can tear the structure apart. Okay, so T, as I said, depending upon your application, can be extremely important, more important than other applied loads. W is the wind load or related internal moments and forces. Okay, so with that, with the notation explained, we come back to the ASD load combinations. And I had a question even before I started saying that the load combination on L sub R, I have shown it as 1, it is 0.75 in BNBC or the other way around, I do not remember. I copied this, literally copied them directly out of BNBC 2020, so there should not be any discrepancy. If there is, I did not mean to inject it. These are supposed to be BNBC 2020 LRFT load ASD load combinations as printed in the code. Okay. We have gravity load combinations. We have gravity plus wind. We have gravity plus earthquake. Okay. If you strip the load combinations of FHT, fluid hydrostatic pressure and temperature effects, which are not always present, this is what the load combinations look like. Okay, look much more reasonable. So the first three, or actually first four, are gravity only. Then you have gravity plus wind and gravity plus earthquake. I hope you see them. And ASD load combinations mean that we use in the load combinations the loads as specified in the code at the service level, so-called. And So in strength design load combination, we will factor those loads up by multiplying with load factors, with the sole exception of earthquake forces. Earthquake forces, as given in the code, are already at strength level. So in ASD load combinations, we take the strength level earthquake forces, divide them by the load factor of 1.4, and 1 divided by 1.4 is rounded to 0.7. That's where the 0.7 comes in. Okay? Every other load, you have 1.0 as the factor of the load. On earthquake forces, it is 0.7, which is 1 divided by 1.4. When we go to strength design load combinations, you will see a factor of 1.0 on E, and on all the other loads, it will be a factor larger than 1. Okay. The 0.75 is because the highest dead loads and highest wind loads are unlikely to occur simultaneously. That's what the 0.75 is supposed to be dealing with. Now, in the old days, at least, we used to take allowable stress increases. In ASD, we look at the stresses caused by the various loads, the combinations of loads. And those stresses, actual stresses, have to be within allowable stresses. We used to take allowable stress increase, particularly when the load combinations included wind and earthquake. That has now become relatively uncommon, and BNBC tells you specifically, unless permitted elsewhere in this code, increases in allowable stresses shall not be used with the loads or load combinations that you just saw. So allowable stress increases shall not be used unless permitted elsewhere in this code. Okay, strength design load combinations. As I said, the difference between strength design and ASD is we are now factoring all the service level loads up, except earthquake, which is already at strength level, that is not factored up. Okay. Load factor on wind is 1.6. I would like to point that out. Load factor on earthquake in the old days used to be 1.4 when our codes used to give us service level earthquake forces. Those days are now gone. Wind is still at service level. The wind velocities that are given in the code will give us surface level wind forces, which we factor up by 1.6 in strength design load combinations. If we strip FHT out of the load combinations, this is what they look like. Okay, so in seismic design, for instance, the important load combinations are 1.2 dead, 0.5 live, no, 1.2 dead, let me see, 1.2 dead, 1.0 live, 1.0 earthquake. This is the so-called additive load combinations. The gravity loads cause bending moment, negative bending moment at the support section of a beam. Earthquake also causes negative bending moment at the support section of the same beam. If we want to figure out the very largest negative bending moment that can happen because of the dead loads, live loads, and earthquake loads, we use this additive load combination. This is the counteractive load combination, dead and earthquake. Dead load still causes negative bending moment at the support section of our beam, but earthquake has now changed direction. It now causes positive bending moment at the same support section of the same beam. If we want to figure out the smallest negative or the largest positive bending moment, we would use 90% of dead plus 1.0 E. That plus will in fact be minus because E has changed direction. Okay, so this is the additive seismic load combination. This is the counteractive seismic load combination. Similarly with wind. Now, some very important things are said that are part of the load combinations. And we are talking specifically here about the strength design load combinations. Effects of one or more loads not acting. Live loads, for instance, do not always have to be present. So effects of one or more loads not acting shall be investigated. The most unfavorable effect from both wind and earthquake. So first of all, you have to consider the fact that live loads may be there, may not be there. Whatever is more unfavorable is what you should consider. Secondly, wind and earthquake are never considered simultaneously. You either consider wind or you consider earthquake, whichever is the worst. That's what you design for. Okay. Then there are a few exceptions to the load combinations that I showed you. So the live load factor in these load combinations is 1.0, but then this exception says that the 1.0 can be taken as 0.5 unless you are designing a parking structure, a place of public assembly, or an area supporting more than 100 pounds per square foot of live load. The 100 pounds per square foot is 5 kilonewton per square meter. I have tried to use all metric on the slides, but metric units don't mean anything to me. So I have to go back to what I'm used to or translate. So when I speak, I may, like I said, 20 feet beam is 100 pounds per square foot, but the actual number in BNBC is 5 kilonewton per square meter. Okay. So anyway, the main and very important thing is that the live load factor, although shown as 1.0 in the load combinations, is typically 0.5 unless you are designing a parking structure, a place of public assembly, or an area supporting heavy live loads more than 100 pounds per square foot. Now, the 0.5 L has been, we have received a lot of questions. Live load is reduced. 40 pounds per square foot of live load for residential occupancy can be reduced to 20 pounds per square foot. Is it proper to apply a load factor of 0.5 on the reduced live load? And the answer is yes. In ACI 318, starting with the 08 edition, we actually added commentary to tell you that it is okay to use the low load factor on the reduced live load. The commentary explains that the reduction in live load is to account for the fact that if you have a large area, it is extremely unlikely that the entire area will be subject to the full design live loads. That's what live load reduction is all about. The larger the area, the less likely it is that the entire area will be covered by the design live loads. The 0.5 load factor on L reflects the reduced probability of simultaneous occurrence of maximum values of multiple transient loads. Okay, maximum live loads, maximum wind, maximum earthquake, those are not going to happen at the same time. And this is why we apply a load factor of 0.5 on the reduced live load. So that's, I think, quite important. Other exceptions. Load factor on hydrostatic pressure H shall be set equal to 0. So if the earth pressure helps, if the bending moment due to earth pressure counteracts earth pressure due to dead loads, the bending moments due to dead loads and live loads, then you shall take the load factor on H equal to 0. That's very important. You are not going to avail yourself of that help. Where lateral earth pressure provides resistance to structural actions from other forces, it shall not be included in H, but you can increase it in the design resistance. How you do it is up to you. But as far as the load combination goes, when H counteracts the effects of dead and live loads or other loads, earthquake forces, wind, the load factor on H shall be taken equal to 0. You shall not take advantage of that help. The final thing is also important. So the 1.6 load factor on 1.6 load factor on wind. That load factor assumes that wind includes directionality effect. When we go to wind loads tomorrow, you will see, we will talk about the directionality of wind. There is a case of D factor which is equal to 0.5 for all buildings. Okay? So when we apply 1.6 on wind, it is wind that includes the 0.15, 0.85 factor. If you get your wind out of ASCE 7 or BNBC 2020, that factor will be included. But there are times when the directionality may not be included in the wind. If you get your wind from wind tunnel testing, directionality may or may not be included. You have to figure that out. If directionality is not included in the wind, if it is not already reduced 15%, then the load factor on the wind should be 1.3, not 1.6. Okay, so this is also, all the exceptions actually are important, and this is why I'm spending time on them. Okay, going beyond allowable stress design and strength design, where required by the applicable, this is now load combinations for extraordinary events. Where required by the applicable code, standard, or authority having jurisdiction in your case will be RAJUK. Strength and stability shall be checked to ensure that structures are capable of withstanding the effects of extraordinary events such as fires, explosions, vehicular impact. This is good to say, but it does not really help you. This is just raising a flag, like this is something you have to think about, but there is no particular guidance that tells you how to do any of these things, how to design for explosions or vehicular impact. Explosions is talked about. There is actually guidance in BNBC, but there are other things on which you don't have guidance. Okay, that brings us to load combinations for serviceability. This, as I said, US codes simply do not have. Anyway, let's take a look. Serviceability limit states of buildings and structures shall be checked for the load combination set forth in this section, as well as mentioned elsewhere. For serviceability limit states involving visually objectionable deformations, repairable cracking, or other damage to interior finishes and other short-term effects, the suggested load combinations for checking vertical deflection due to gravity is just the service level dead load plus the service level live load. Okay. So if you are concerned about visually objectionable deflections, repairable cracking, etc., that's your load combination for considering vertical deflection. Service level dead load, service level live load. This is when you use that load combination, you are thinking about immediate deflections caused by the loads. You load the structure, there is immediate elastic deflection. That's what you are thinking of. Okay? For serviceability limit states involving creep, settlement, similar long-term permanent defects, the load combination that is being suggested is dead plus 0.5 life. And the deflections due to dead loads have to be amplified by a time-dependent factor. Okay, so the dead load effect used in applying combinations 1 and 2 above may be that portion of dead load that occurs following attachment of non-structural elements. That is well said. But then in applying this this load combination, dead plus 0.5 live, to account for long-term creep effect, the immediate deflection may be multiplied by a creep factor ranging from 1.5 to 2. In SCI 318, there is a time-dependent factor that goes up to 2, and most people believe that 2 is not even enough. So the effect, the deflection caused by dead load shall be multiplied by 2 to account for long-term effects, and then you add the immediate deflection caused by half the service level live load. And that's the deflection you consider when time-dependent effects are involved. Now, there are deflection limits given in table 1.2.5. It is not my intention to take you through the table, but the fact is that there are limitations, root members. So immediate deflection caused by live load shall be limited to certain things. The wind deflection I'll talk about next separately, and then dead plus live. So this will be also immediate deflection caused by dead and live loads. These notes to go with table 1.2.5 are quite important, and I do not have time to take you through. There is one for aluminum, one for wood. You may not care much about them, but there are very important other notes. In using that table, these notes become very, very important. Okay. Now let us come to something I want to emphasize that I do. This is an important topic that I want to spend a little bit of time on. For serviceability limit state against lateral deflection of buildings and structures. So far we were talking about gravity deflection. For serviceability limit state against lateral deflection of buildings and structures due to wind effect, the following combination shall be used. Okay, dead plus 0.5 live sitting on the structure. This is gravity. And then you apply 70% of the wind load specified in the code on the structure. Why 70%? That is the first important question. Okay, this 0.7. The wind that is specified in BNBC 2020 has a 50-year return period on it. The wind velocities that are plotted in the code are 50-year return period wind velocities. In serviceability check, 50 years is considered to be too long. Serviceability should be checked under much more frequent wind, not something that may happen once in 50 years. The number that most people like to use is wind that happens 1 in 10 years, 10-year return period wind. The 0.7 factor converts the 50-year return period wind down to 10-year return period wind. That's where the 0.7 comes from. Okay, so you apply dead and 0.5 live on the structure, and then you hit the structure with 70% of the service level wind, bringing it down to 10-year return period wind. Okay, and under that combination, the the lateral deflections have to be within certain limits. Okay, the limits are, this is something I absolutely want to talk about. The overall sway at the top level of the building or structure due to wind loading shall not exceed 1 over 500 times the total height of the building above ground. So total height divided by 500 is the limit on the total deflection at the top of the building due to wind. The 70% of W. Okay. Now, what I do want to say is that in US codes, we have never had a limit like this. Okay. Various design offices have their own criteria, and height over 500 is very popular. But when we say height over 500 in a typical US design office, they will not decrease the W by 0.7. Okay, so that is one difference. Secondly, and more importantly, we have never imposed a limit in the code because the calculated deflection depends on your stiffness assumptions. And the stiffness assumptions have been very difficult to pin down. We have found it very difficult to agree on a set of stiffness assumptions that can be specified in the code using which you will calculate your deflections. Okay? But anyway, BNBC has gone ahead and given you a limit on total deflections caused by wind. Now then, then there is another part which I think is I do not understand, and I do not believe it is right. So the second part of this is talking about story drift. Story drift is the horizontal displacement of one level of a building or structure relative to the level above or below. So it is deflection at the top of a story minus the deflection at the bottom of the same story. That is story drift. Calculated story drift shall include both translational and torsional deflections and conform to the following requirements. So if there is torsion, that may contribute to the inter-story drift that we are talking about. Deflection at the top of the story minus deflection at the bottom of the same story. Now, in this section 1561, BNBC has given you limits on inter-story drift under loads other than earthquake loads. This I have never ever seen in US code or anywhere else. Okay? In seismic design, this is one of the main things we do. We limit inter-story drift. And that inter-story drift has a specific definition that I will share with you next week. But in non-earthquake design, I have never ever seen a limitation on story drift. That's number one. Number two, this is something I absolutely do not understand. The limitations on story drift, this is inter-story drift, deflection at the top of a story minus deflection at the bottom of the same story, is given in terms of the building height, not story height. And that I find to be totally like, I do not understand. And in all due respect, I do not believe this makes any sense. How do you put a limit on inter-story drift based on the total height of the structure? It has to be story height. I honestly do not understand this. So I did want to point this out. So there is one limit for the more rigid building, short period buildings, and there is another limit for the longer period buildings, which is well and good. and a very tight limit for unreinforced masonry structures, which also makes sense. But limits on interstory drift in terms of total building height, I absolutely do not understand. The drift limits above may be exceeded where it can be demonstrated that greater drift can be tolerated by both structural and non-structural elements without affecting life safety. For earthquake loads, the story drift shall be. So earthquake story drift we will talk about the next day. Okay, so that at long last brings us to the loads themselves. We just went beyond the load combinations. I see that I have spent just about an hour, which is fine. I think to my mind, everything I tried to point out is quite important. Okay, so now the loads that are specified in BNBC 2020, dead loads. Definition, remember, was part of the notation D. Some of that is repeated here. Dead load is the vertical load due to the weight of permanent structural and non-structural components and attachments of a building, such as walls, floors, ceilings, permanent partitions, and fixed service equipment, etc. Permanent partitions are included in dead load. Movable partitions are live load. And then fixed service equipment, everything that is on the structure, HVAC, water tank, all of that is dead load. Assessment of dead load. So dead load for a structural member shall be assessed based on the forces due to weight of the member itself. This is dead load on a member. Weight of the member itself, weight of all materials of construction incorporated into the building to be supported permanently by the member, weight of permanent partitions, weight of fixed service equipment, and interestingly, net effect of pre-stressing. Okay, this is specifically mentioned. So the effective pre-stress shall be dead load. I think you are very lucky that BNBC gives you these weights of materials and construction for calculation of dead loads. We do not have that in ASCE 7. So in estimating dead loads, the actual weights of materials and construction shall be used, provided that in the absence of definite information, the weights given in the two tables that we are talking about shall be assumed for the purposes of design. So if you have better information, you are free to use it. If you don't use the values in the table, there is a table of unit weight of basic materials. There is another table, weight of construction materials. So one is basically density, unit weight. The other is load in something like pounds per square foot. Both tables, I think, are extremely good to have. And the fact that they're included in the code, I think, is kind of nice. Weight of permanent partitions. When partition walls are indicated on the plans, their weight shall be considered as dead load, acting as concentrated line loads in their actual positions on the floor. Very, very specific, and that makes a lot of sense. The loads due to anticipated partition walls, which are not indicated on the plans, shall be treated as live loads and determined in accordance with the next section, the live load section 2.3. Okay? So loads due to anticipated partition walls which are not indicated on the plan shall be treated as live loads. Fixed service equipment. Fixed service equipment and other permanent machinery such as electrical feeders, heating, ventilating, air conditioning systems, lifts and escalators, Plumbing stacks risers shall be included as dead load whenever such equipment are supported by structural members. Okay? So additional loads. This is something I find very interesting. So in evaluating the final dead loads on a structural member for design purposes, allowances shall be made for additional loads resulting from: number one, difference between the prescribed and the actual weights of the members and construction materials. Difference between prescribed and actual. Two, inclusion of future installations. Three, changes in occupancy or use of buildings. Four, inclusion of structural and non-structural members not covered in the earlier sections. This I frankly have never, this is very unusual for an engineer to consider. What I have seen, and this is quite common, somebody is designing an office building, the live load in AC 750 pounds per square foot, but there is expectation that the building will be sold down the line, and you do not know that somebody will not move a library into some of the spaces. So instead of 50 pounds per square foot, the designer would design for 70 or 80 pounds per square foot of live load. This is quite common. Uh, and that makes a lot of sense, gives the owner a lot more flexibility when it comes to selling or change of ownership. But this advice on dead loads, I do not believe that many engineers think in those terms. Okay, that brings us to the live load section. Definition of live load. Live load is the load superimposed by the user occupancy of the building, not including environmental loads such as wind, rain, earthquake, and not including dead load. Okay. So once again, going back, live loads are the only user imposed loads. Live loads are the reason why we put up a structure. Okay, so please remember that for all time to come. Live loads are extremely important, and you have to pay proper attention to the live loads that you are designing for. And and this dead loads don't change from one code to another, to one edition to another. Live loads, on the other hand, if you look at ASC 7 editions going back, things have changed. I wouldn't say drastically, but there are changes being made in every edition. Anyway, minimum floor live loads. Minimum floor live loads shall be the greatest actual imposed loads resulting from the intended user occupancy of the floor, shall not be less than uniformly distributed load pattern specified in section such and such. The live load shall be assumed to act vertically upon the area projected on a horizontal plane. Okay, that is again kind of important. Live load shall be assumed to act vertically upon the area projected on a horizontal plane. If you have an inclined surface, that is important to remember. So the main thing is that there is a table in the code, and this is true of IBC, this is true of ASC 7. The table gives you minimum uniformly distributed and concentrated live loads. Okay, this is table 6.2.3. BNBC 2020 has decided to split, not to put the roof live loads in this table. Roof live loads are given in a separate table, 6.2.4, the next table. So this table is, I would say, one of the most important parts of the structural one of the most important items in the structural chapters of the code. The minimum uniformly distributed and concentrated live loads. Okay, so the uniformly distributed live load shall not be less than the values listed in the table, reduced as may be specified. So the tabulated values of live load may be reduced, applied uniformly over the area of the floor or any portion thereof to produce the most adverse effects in the member concerned. Concentrated loads. So the table gives you uniformly distributed loads and also concentrated loads. Both are not supposed to be applied at the same time. You apply the distributed loads, you separately apply the concentrated loads, and you design for the worst effects. That's the idea. The concentrated loads to be applied non-concurrently, that's important. That's what I was trying to stress. With the uniformly distributed load shall not be less than the values listed. Unless otherwise specified, the concentrated load shall be applied over an area of 300 by 300 millimeter. That's only 12 inch by 12 inch. I find this to be a little bit I don't know strange, but it is quite different. In AC7, going back to '05 edition, on which most of the structural provisions of BNBC 2020 is based, we use 2.5 feet by 2.5 feet, 30 inches by 30 inches, much bigger area. So smaller area obviously is worse. You have much higher stresses. So anyway, I did want to point that out. So the concentrated load shall be applied over an area of 300 millimeters by 300 millimeters shall be located so as to produce the maximum stress conditions in the structural members. In areas where vehicles are used or stored, such as car parking garages, ramps, etc., there are detailed provisions given that I chose not to go into. Partition walls. When partitions not indicated on the plans are anticipated to be placed on the floors, their weights shall be included as an additional live load acting as concentrated live loads in an arrangement producing the most severe effect on the floor unless it can be shown that a more favorable arrangement of the partition. This is quite a bit, but it's totally understandable upon reading. So when partitions not indicated on the plans are anticipated to be placed on the floors, then you do these line loads and so forth. Much more common is these light partitions that are movable. In the case of light partitions, wherein the total weight per meter run is not greater than 5.5 kilonewtons, a uniformly distributed live load may be applied. Okay, such uniform live load per square meter shall be at least 33% of the weight per meter run of the partition, subject to a minimum of 1.2. So the bottom line is minimum of 1.2 kilonewton per square meters. I believe that is about 25 pounds per square foot. We designed for a much lighter 15 pounds per square foot. So this 1.2 kilonewton per square meter minimum partition load is quite a bit. 25 is quite high. I actually never remember a time when we used 25 pounds per square foot. Anyway, so that's your requirement, 1.2 kilonewton per square meters. If you have more than one occupancy, two or more occupancies at different times, the value to be used from the table shall be greatest value for any of the occupancies concerned. Minimum roof live loads. We are now going to roof live load from floor live load, which is the table that I was talking about. As I mentioned, you have a separate table for roof live loads. So roof live load shall be assumed to act vertically over the area projected by the roof. So this is on horizontal projection. or any portion of it upon a horizon, and shall be determined as specified in table 6.2.4. That's the roof live load table. In AC 7, one table gives you floor live load and roof live load. Then there is a section on live loads not specified. Live loads not specified for uses or occupancies shall be determined from loads resulting from weight of the probable assembly of persons, weight of the probable accumulation of equipment and furniture, and weight of the probable storage of materials. Okay, all of those things contribute to live load. The partial loading and other loading arrangement, I am not going to read. It tells you the right things. If you go back to strength of materials, that's what we have been taught to do. But in design offices, I can tell you, at least in US design offices where labor is very expensive, this is seldom done. So I'm not telling you don't worry about it, but I'm just giving you a bit of a perspective. Okay, so partial loading and other loading arrangements. Other live loads on miscellaneous structures and components, such as handrails and supporting members, parapets and balustrades, ceilings, skylights, and the like, shall be determined from analysis of the actual loads on them, but shall not be less than those given in. So there is another table, miscellaneous live loads, which I think is quite important. AC7 does not have a table like that, but some of the items in the table, like the in car parks, the curbs, or how the word doesn't come to me, the impact of the cars on the barriers on the site, those things are covered in AC7 separately, and they are in the table. So this 6.2.5 miscellaneous live loads, to me, is something that you should not overlook. Many structural engineers may not have to deal with that, but some do. And if you have to deal with that, that is an important table. Then this is something I think, just like I talked about the dead load tables being given in the code, I think you are lucky. This is another thing on which US standard does not give you specific guidance, but you have specifics given, which is very nice. So impact and dynamic loads. The live loads specified, the live loads that we were talking about in the big table shall be assumed to include allowances for impacts arising from normal uses only. So impact is included, but impact from normal uses. However, forces imposed by unusual vibrations and impacts resulting from the operation of installed machinery and equipment shall be determined separately and treated as additional live loads. Okay, so imposed by unusual vibrations and impacts resulting from operation of installed machinery and equipment. Live loads due to vibration or impact shall be determined by dynamic analysis of the supporting member or structure, including foundations, or from the recommended values supplied by the manufacturer of the particular equipment or machinery. The dynamic analysis is far from simple. The manufacturers, this is how it typically goes. You get numbers or suggestions or recommendation from the manufacturer. In the absence of definite information, values listed in table 626 are for some common equipment shall be used for design purposes. And I think this is a very nice table to have. I reproduced the table because I liked it so much. So lifts, hoist-related operating machinery, so vertical load that you are designing for shall be increased 100% because of the impact. That's what this is saying. Light machinery, 20%. Reciprocating machinery or power-driven units, 50%. So this is a very nice set of recommendations that the code has given you. Unless you know any better, unless your manufacturer can give you more informed recommendations, these are things you can fall back upon, which is very nice to have. Okay, reduction of live loads, very, very important topic. Live load reduction goes a long way back, and live load reduction used to be based on tributary area, which I think all of us understand, tributary area. But at one point, for the 95 edition of ASCE 7, the committee decided that influence area was better than tributary area, the area that influences the load on a structural member, as opposed to tributary area, which is the area that brings load onto the structural member. So the live load reduction equation became what you see on the slide. L sub 0 is the unreduced live load, L is the reduced live load, and the reduction is a function of square root of the influence area. Reduced design live load shall not be less than 50% of the unreduced live load per member supporting one floor, nor less than 40% of L sub 0 per member supporting two or more floors. So for columns, you can go down to 60% of the unreduced live load. For beams and slabs, 50% of the unreduced live load. Influence areas were illustrated in the commentary to ASCE 7. And I think the picture is very, very nice, very clear picture. Okay? The load on this beam is influenced by those two areas, as opposed to tributary area, which will go from here to there. Okay? So the load on this beam is influenced by that area. That's what influence area meant. But this, even with this figure, it caused a lot of confusion, particularly when you had overhangs and things. What is the influence area? Engineers had trouble figuring out. So in the next edition, dated 1998, ASCE 7 kept the formula, but now expressed influence area as a function of tributary area. Tributary area is something people apparently understood. So now ASCE 7 said that influence area that we talked about in the previous edition shall be a multiple of the tributary area. And this multiplier, K sub LL, was given in ASCE 798. BNBC 2020 uses this formula out of ASCE 705 and uses the same table of K sub LL that I'm going to show you. The same limitations apply. The live load reduction shall not exceed 50% for beams and slabs, nor 60% for columns and walls. ASCE 7 starting in 98 have had this picture in the commentary. The tributary area is shown in red, and the influence area for the same structural member is shown in gray, and you see where this K sub LL is coming from, and there are overhangs in the picture. So with that, ASCE 7 definitely hoped that confusion would be avoided. This is the table of K sub LL for an interior column. The influence area is 4 times the tributary area. For an exterior column without cantilever slabs, it is 4 times. For edge columns, the influence area is 3 times the tributary area, and so forth. Limitations on live load reduction. Heavy live loads. Live loads that exceed 100 pounds per square foot. I think previously we said 5 kilonewton per square meter. Here is 4.8, whatever, 100 pounds per square foot, shall not be reduced. Exception, live loads for members supporting 2 or more floors may be reduced. So on a column, you get up to 20% reduction, even when live load is heavy, exceeding 100 pounds per square foot. But otherwise, no reduction of heavy live loads. Passenger car garages, you have the equivalent of 40 pounds per square foot in the table, and that live load is non-reducible. So the live load shall not be reduced in passenger car garages. This is something that has evolved and changed in US standards, but BNBC 2020, this is what you use. Passenger car garages, no reduction of the live load that is listed in the table. Live loads per member supporting 2 or more floors may be reduced by 20%. Special occupancies. Live loads of 100 pounds per square foot or less shall not be reduced in public assembly occupancies. Okay, public assembly. There shall be no reduction of live loads for cyclone shelters. One-way slabs, the tributary area is up T for one-way slabs shall not exceed the area defined by the slab span times a width normal to the span of 1.5 times the slab span. Okay, so if you have a one-way slab, then there is a limitation on the tributary area for live load reduction purposes that you need to be aware of. Roof live load, the minimum uniformly distributed roof live load. I forgot to change this table number. Sorry, this is an IBC table number. I have to do that. You know the table. I don't remember the number by heart. This is roof live load reduction. Depends on the tributary area and also the slope of the roof. So for area less than or equal to 18.58 square meters, no reduction. Between 18.58 and somehow interestingly here at this location, many other locations, I see that BNBC has made a soft metric conversion from the ASC 7 numbers. Other cases, it is hard metric. The numbers are rounded off. Anyway, so between 18.58 and 55.74 square meter, this is the live load reduction due to area, and larger roofs, it is 0.6, 40% reduction. Depending upon the slope, the F is defined here, and again, you go from 1 to 0.6. I think if you look at the slide, the details are clear. So roof live load reduction has 2 parts, one dependent on the area of the roof, the other dependent on the slope of the roof. Special purpose roofs, roofs that have an occupancy function such as roof gardens, assembly purposes, or other special purposes are permitted to have their uniformly distributed live load reduced in accordance with the floor live load reduction. Those special purpose roofs, if you are going to have meetings, assembly of people on your roof, then you cannot design for 20 pounds per square foot of roof live load. You have to design for assembly load. And assembly live load cannot be reduced, but there are other live loads. If you have a roof garden, well, if you decide to sleep on your roof, for instance, you should design it for 40 pounds per square foot, not 20. And that 40 pounds per square foot will be reducible. That's what we are trying to say here. Okay, I threw in a little bit of an example. I don't know if we are having a time problem, but I'll take you through this a little bit. So these numbers may not be important. This is a very simple floor plan of a load ice. I'm sorry. I don't know why this popped up. Okay, it will go away, hopefully.
Go back.
Uh,
Or did you want to go back?
maybe just do. Oh, okay, it went away. Okay, thank you. So this is the simple plan of the building. There are shear walls on the two faces. Otherwise, there are columns, interior columns. There are 3 spans of 8 meters this way, 2 spans of 7 meters this way. Okay, and I will show you live load reduction for this column, and the here it is supposed to be a shear wall. The interior part is missing. So there are 2 exterior shear walls, 1 interior shear wall, and I will show you live load reduction for this interior shear wall. Okay. So this is the you see the elevation of the building. Now a couple of the reason I wanted to go to the numbers is a couple of reasons. So this is floor 1, floor 2, and this is the roof. Okay, I didn't number it. In Bangladesh, I think so. This will be the numbering in Bangladesh. Here in the US, this should be floor 1, the ground floor. This should be 2, this should be 3. But anyway, for our purposes, this is floor 1, floor 2, and this is the roof. The point that I'm making is that the roof area does not count in tributary areas. So this is a corner column. The tributary area is this, which will be half of the 8 meters, 4 meters, and half of the 7 meters, which is 3.5. So this is 14 square meters. 14 square meters, and the lower level column will be supporting 2 floors, so it is 28 square meters. Unreduced live load 2.4 kilonewtons per square meters. K sub LL for that corner column is 4. K sub LL times A sub T gives you 56 and 112. Using the formula that I showed you, you get 13.9% reduction, 31.8%. Maximum reduction is 50% for a column supporting 1 floor, 60% for a column supporting 2 floors, 13.9% governs 31.8. So these are the reduced live loads. The interior shear wall, the tributary areas are 112 and 224. The roof doesn't contribute. The unreduced live load is the same. K sub LL is 1. This is K sub LL times A sub T. The reductions are 31.8, 44.5. The maximum do not govern. So the reduced live loads are these. Very simple numbers. Hopefully this is done right, and hopefully this will help you a lot. Can partition load, the movable partition loads, 25 pounds per square foot in your case, be reduced since they are live loads? Nowhere does BNBC 2020 say explicitly that partition loads cannot be reduced. However, it is believed that it cannot be reduced because it is not listed in the table. My belief is that only the tabulated values can be reduced. Okay, beyond dead and live loads, the loads treated are miscellaneous loads, rain, flood and surge, temperature effects, soil and hydrostatic pressure, and the specialized loads I'm not going to discuss with you, I mentioned, and the erection and construction loads. So I do want to take a quick look. I have roughly a half hour left. I think the timing will work out. Okay, rain loads. I have to think a little bit how I'm going to manage the time. The rain loads, I found rain loads are obviously important. Dhaka area, flood and surge definitely is not there. Flood, I don't exactly know. I do not believe it's a major consideration, but rain loads obviously cannot be ignored. You design for the larger of roof live loads and rain loads. If rain loads are smaller than the roof live loads, 20 pounds per square foot or whatever, doesn't count. But if the rain loads are higher, you have to design for the higher loads. Now, what is given in BNBC 2020, I think, is grossly inadequate for design purposes. So I included information here based on ASC 716, which is the last one out in print, and whether I will take you through, take the time to take you through, I'll have to figure out. Anyway, let's look at what BNBC has for rain loads. Rain loads shall be determined in accordance with the following provisions. Each portion of a roof shall be designed to sustain the load from all rainwater that could be accumulated on it if the primary drainage system for that portion is undersized or blocked. Ponding instability shall be considered in this situation. Ponding instability is something I decided not to go into. That's when the roof is deflected, and because of the rainwater and the ponding of the rainwater, then the accumulated rainwater then causes further deflection, and this can cause serious problems. So the solution is really drainage, but anyway, ponding instability is something that has to be investigated. ASC 7 says that, BNBC says that. Roofs equipped with controlled drainage provisions shall be designed to sustain all rainwater loads on them to the elevation of the secondary drainage system plus 1/4 kilonewton per square meter. Ponding instability shall be considered in this situation. So this is, I said grossly inadequate. That was probably overstated. What I find to be, anyway, let us look at this one more time. So roofs equipped with controlled drainage provision shall be designed to sustain all rainwater loads on them to the elevation of the secondary drainage system plus 0.25 kilonewton per square meter. Okay. Now let us look briefly at what we have in ASC 716, and I have gone a little bit beyond. So ASC 716, each portion of a roof shall be designed to sustain the load of all rainwater that will accumulate on it if the primary drainage system for that portion is blocked, plus the uniform load caused by water that rises above the inlet of the secondary drainage system at its design flow. So rainwater that will accumulate on it if the primary drainage system is blocked. BNBC says that, AC7 says, plus the uniform load caused by water that rises above the inlet of the secondary drainage system at its design flow instead of a fixed 0.25 kilonewton per square meter. Okay. Then it tells you rain load is 0098 in your units, SI units, D sub S, the static head, plus the hydraulic head, D sub H. If the secondary drainage system contains drain lines, such as lines and their, so rain load shall be based on the total head, static head D sub S plus hydraulic head D sub H associated with the design flow rate for the specified secondary drains, etc. So this is the governing equation. You want to calculate design rain loads. It's a constant times the static head plus the dynamic head. Okay. So static head and dynamic head, what are these? So this is the roof level. This is the primary drain that we are talking about, and the secondary drain is just this dam. Okay, if water rises beyond that, then water spills over. Static head is simply this distance. Okay, to the from here, the depth of the primary drain bowl is so this is the roof. This is the top of the dam, which is your secondary drain, and this is the rainwater that is trying to go through the drain. The static head is from the roof to the top of the secondary drain, D sub S as marked here. The hydraulic head is this, okay, from the top of the secondary drain to how far the water can rise on the roof. So we have to design the roof for the static head D sub S plus the hydraulic head D sub H. D sub S part is simple. The D sub H, the hydraulic head, is not that simple. Now, it is entirely possible that BNBC is giving you the 0.25 kilonewton per square meter for the hydraulic head. That's the total weight of rainwater because of the hydraulic head. It is entirely possible. I do not know. So the depth of water D sub H above the inlet of the secondary drainage system is the hydraulic head in reality is a function of the rain load intensity I at the site, the area of roof serviced by the drainage system, and the size of the drainage system. So this is the equation that you find, I forget now, I think this is in the commentary to AC7 rain load provisions. So the flow rate Q is a constant times the area that contributes to the rain load going through the drain, and I is the rain load intensity. So the rain load intensity figures in. The rain load has to, the design rain load has to be a function of the rain load intensity. This is what is missing in BNBC 2020. This is why I decided to go into AC 716 to tell you about the tie-up. So the hydraulic head D sub H depends on the flow rate, which depends on A and I being the rain load intensity, and A being the area contributing to the rain load going through the drain. So A is tributary roof area plus 1/2 of the wall area that diverts rainwater onto the roof, serviced by a single drain outlet in the secondary drainage system. I is design rainfall intensity in millimeters per hour. Yeah. The design rain load intensity, where does it come from? And what rain load intensity are we talking about? This is important stuff. The usual design rain load uses a 60-minute duration, 100-year return period rainfall event for the design of the primary drainage system, 60-minute duration, 100-year return period for the primary drainage system. 15-minute duration, 100-year return period rainfall for the secondary drainage system. There is a NOAA, National Oceanic and Atmospheric Administration, a federal agency website that gives you the rainfall intensity for all kinds of durations and all kinds of return periods. So for any US location, you can go to that website and find the rain load intensity for the duration you want and the return period you want. With the rain load intensity, you can figure out the flow rate, and with the flow rate, you can figure out the hydraulic head. And the hydraulic head plus the static head gives you the rain load that you design your roof for. Okay. Obviously, BNBC does not tell you all of this, does not relate the rain load to the rain load intensity. So I kind of found it to be inadequate, and I would like to know more about how the BNBC provisions are being implemented. Okay, let's go on to loads due to flood and surge. Flood loads on structures at inland areas, that would be Dhaka. For structures sited at inland areas subject to flood, loads due to flood shall be determined considering hydrostatic effects, which shall be calculated based on the flood elevation of 50-year return period. Okay, this is very specific. For now, where that exactly comes from, I do not know. I have not inquired. In the US, it is Federal Emergency Management Agency that will give you that kind of information. For riverside structures such as that under exposure C, this is wind exposure C that we will talk about tomorrow. Hydrodynamic forces arising due to approaching wind-generated waves shall also be determined in addition to the hydrostatic load on them. In this case, the amplitude of such wind-induced water waves shall be obtained from site-specific data. So this already is getting pretty complicated for riverside structures such as under exposure C. So again, I do not know that flood loading is a big concern in the Dhaka area, and if it is, I do not know how this BNBC provision is being implemented. But I today am not going to go beyond that. I'm not trying to go beyond that. As far as surge goes, high surge risk areas are in South Bengal, the bright red in this map. The not so high surge risk areas are the pink on the map. Obviously, Dhaka is far removed, so this tidal surge is not a concern in design that RAJUK will have to check. Temperature effects. Let us go through what the BNBC has, and I will add my kind of perspective on that. So temperature effects, if significant. Now before I go in, I would remind you again The term in the design load combinations is T. T is definitely for temperature effect, but T represents much more than temperature effect. It is, again, this is probably the fifth time I'm saying this, it is the effect of restrained volume changes. Please always think in those terms. It is the effect of restrained volume changes. The volume changes may be due to temperature change. It may be due to shrinkage of concrete. It may be due to creep of concrete. It could be a lot of things. Okay, so temperature effects, if significant, shall be considered in the design of structures or components thereof in accordance with the provisions of this section. In determining the temperature effects on a structure, the following provisions shall be considered. The temperature indicated shall be the air temperature in the shade. The range of the variation in temperature for a building site shall be taken into consideration. Now, what I found just reading this is range of temperature variation. It does not tell you from day to night. That is a variation that we consider. We also consider seasonal variation. What is the lowest temperature during the year? What is the highest temperature during the year based on lots of records? Both one or the other or both need to be considered depending upon the application. Effects of the variation of temperature within the material of a structural element shall be accounted for by one of the following methods. Relieve the stresses by providing adequate numbers of expansion or contraction joints. That is not a bad solution. That actually, in fact, is a good solution. You avoid the problem. But the joints that are being talked about are very difficult to maintain through the lifetime of a structure. They are likely to be liable to be a headache through the lifetime of the structure. So we do not really favor joints. There are port strips and things that can serve the same purpose. Port strips would be you cast a stretch of concrete, then you leave a couple of feet open, the reinforcement is continuous, then you pour the next strip and so forth. And then after most of the shrinkage has taken place, you come back and fill the gaps that you kept. So these are called pour strips, and that way we have been very successful in getting rid of the effects of shrinkage in structures. Now, if you go beyond 500-600 feet, you have to have joints, but up to something like 500 feet, we can do without joints. But joints or something like the joints, which would be the pour strips, is a good solution. This is one way to avoid the problem or design the structural element to sustain additional stresses due to temperature effects. When the second alternative is considered to be, okay, the structural analysis shall take into account the following: the variation in temperature within the material of the structural element, exposure condition of the element, and the rate at which the material absorb or irradiate heat, the warping or any other distortion caused due to temperature changes and temperature gradient in the structural element. All of this is extremely difficult to do. We had, I remember, not too long ago, a little bit of a job from Dubai, advising somebody on how to account for temperature effects in their structures. They were having problems with the local authorities. And we found it extremely difficult to come up with come up with actual advice that would be acceptable to the jurisdiction and would do the designer any good. So all of these things are easy to say, but much more difficult to do. Now, as I said, precast people deal with volume changes all the time. So I am not suggesting that the effects of restrained volume changes cannot be dealt with, but the preferred solution is to avoid the problem. Now, here you are talking about joints, cast in place concrete. That's what it has to be. If it is precast, what you have to watch out for is you cannot restrain two ends of a precast member. Okay, then you are in trouble. Then the member will try to do one thing that you are not letting it do. So one member can be restrained, the other member you have to let it move, and that may be a slotted connection or something sitting on a bearing pad or whatever. So that is the key thing. It's not a joint as such, but you let you don't restrain two ends of a member. That probably the key thing that I'm trying to tell you. When it can be demonstrated by established principle of mechanics or by any other means that neglecting some or all of the effects of temperature does not affect the safety and serviceability of the structure, the temperature effect can be considered insignificant and need not be considered in design. This is a good thing that the code tells you that. The big perspective that I want you to have is once the envelope goes on, once a building is enclosed, the temperature effects are not all that significant. In this country, everything pretty much is air conditioned. So once a building is enclosed, the temperature variation and so forth inside the building is very little. In Bangladesh, that's not probably true to the same extent. And at the same time, inside your home, you will not have major variations in temperature. It cannot be tolerated. You will close the window, do whatever needs to be done to, okay. So the problem of temperature variation is open parking structures or structures during construction. Structures during construction, the best thing is protection. You actually insulate however you can, so that the temperature effects do not mess up your construction. So hopefully some of the things I said make sense to you and will help you. So temperature effect or effects of restraint volume changes, you have to have sense. You have to know what you are dealing with, and you have to look for practical solutions rather than calculating and designing for it, which can be done, but it cannot be easily done. Okay, soil and hydrostatic pressure. For structures or portions thereof lying below ground level, loads due to soil and hydrostatic pressure shall be determined in accordance with provisions of this section, applied in addition to all other applicable loads. So pressure on basement wall. In the design of basement walls, similar vertical or nearly vertical structures below grade, provision shall be made for the lateral pressure of adjacent soil. Allowance shall be made for possible surcharge due to fixed or moving loads. So if there are things on the surface, that obviously has to be considered, the weight of those. When a portion or the whole of the adjacent soil is below the surrounding water table, this is important, computation shall be based on the submerged unit weight of soil. So this will be saturated soil plus full hydrostatic pressure. Okay? So that's important thing that is said there. This is on the wall. If you're talking about floors that are under the ground level, in the design of basement floors and similar horizontal or nearly horizontal construction below grade, the upward pressure of water, this is buoyancy, whatever you want to call it, if any, shall be taken as the full hydrostatic pressure applied over the entire area. The hydrostatic head shall be measured from the underside of the construction. So this can be quite important, the upward pressure of the water on the floor, and that obviously has to be considered in design. Now here I brought in the IBC a little bit. This is actually, I took it from 2021 and then forgot to change the date. 2021 has more than 2018 had. So it talks about lateral pressure. I don't know if it is necessary to read. The main reason I went into it may not be a bad idea. It won't take long. Okay, foundation walls and retaining walls shall be designed to resist lateral soil loads from adjacent soil. Almost the same thing as BNBC. Soil loads specified in table such and such. BNBC doesn't give you this table. That's the main reason I wanted to show you this. Shall be used as the minimum. Soil load specified in the table shall be used as the minimum design lateral soil loads unless determined otherwise by geotechnical investigation in accordance with section 1803. Most of the time in US, the soil lateral load will come from the geotechnical engineer. But in the absence of that, IBC gives you a table which will enable you to calculate the soil lateral pressure. Okay, this is why I wanted to show you the IBC provision. Foundation walls and other walls in which horizontal movement is restrained at the top, and that is typically the case because there is a floor at the top, the slab on grade, whatever you have. So foundation walls and other walls in which horizontal movement is restricted at the top shall be designed for at-rest pressure, as we call it. Retaining walls free to move and rotate at the top shall be permitted to be designed for active pressure. There is active pressure and at-rest pressure. Lateral pressure from surcharge loads shall be added to the lateral soil load. This was said in BNBC. Lateral pressure shall be increased if expansive soils are present at the site. This was not in BNBC. This is a problem in many parts of this country. The soil is expansive and that causes its own problems. Foundation walls shall be designed to support the weight of the full hydrostatic pressure of undrained backfill unless a drainage system is installed in accordance with such and such. So this will give you a bit more of a perspective. I do want to show you the table. There is an exception to the lateral pressures that are, so foundation walls extending not more than 8 feet below grade and laterally supported at the top by flexible diaphragms shall be permitted to be designed for active pressure, okay, instead of at-rest pressure. Uplift loads on floor and foundations. This was not in 2018 IBC. This has been added. Basement floors, slabs on ground, foundations, similar approximately horizontal elements. This is in BNBC, but was not in IBC until now. Shall be designed to resist uplift loads where applicable. The upward pressure of water shall be taken as the full hydrostatic pressure applied over the entire area. This is BNBC almost word per word. The hydrostatic load shall be measured from the underside of the element being evaluated. The design for upward loads, cut it off mid-sentence without meaning to. Anyway, this is the table I wanted to show you. On unified soil classification, those are used widely. And then design lateral loads, active pressure and at-rest pressure are given. Obviously, these are in American units. But I did want to show you, just like BNBC has dead load tables that we do not have, the impact load allowances that we do not have. This is something IBC has that BNBC does not give you. You are on your own in figuring out. Obviously, you have to go through a geotechnical engineer. Okay, so beyond soil and hydrostatic pressure, there are loads due to explosions, vertical forces on air raid shelters, and loads on helicopter landing area that I said I will not talk about. Those are specialized. That leaves us with erection and construction loads. And this is what BNBC has to say. All loads required to be sustained by a structure or any portion thereof, due to placing or storage of construction materials and erection equipment, including those due to operation of such equipment, shall be considered as erection loads. Provision shall be made in design to account for all stresses due to such loads. This is, again, grossly inadequate. That does not tell you exactly what you are supposed to do or how to do it. At the same time, I want to say a couple of things. Building codes typically do not cover what we call means and methods of construction. Do not cover them. Means and methods of construction are outside of the scope. In US, there is ASCE 37, a different standard, totally different from ASCE 7 that we have been talking about. That talks about construction loads. That is an important standard that is widely used. You may want to take a look at that. The only other thing that I would want to say is that a structure experiences, at least a building structure experiences, the worst loads it will ever see during its construction. In other words, if a structure survives its construction, chances are very high that it will be around for a long time in the absence of unusual events like earthquakes or cyclones. And most of this, the worst of the loads as far as the concrete structure is concerned, comes from premature removal of temporary supports. So you cast a floor, it is supported on some kind of props, okay? And it is in the contractor's interest to remove those props for reuse as soon as he can. And if those are prematurely removed, the concrete is green. A long span of green concrete left unsupported may result in disaster, or at least it can cause injury to the concrete. And you may have problems down the life of the structure. So please keep this in mind, that the construction phase is very important. The temporary support system is very important. To keep the temporary supports in place for long enough is very important. Do not underestimate. Those are never codified. I have never ever seen those things codified. That would be extremely difficult to do. At the same time, those are extremely important considerations. The engineer has to have experience, and the people inspecting have to have experience for you to successfully conclude the construction, particularly of a concrete structure. To an extent, this is true of masonry as well. Okay, that's where I think I will end today's presentation. It's almost on the dot where we plan to end it, and I think we have 15 minutes for questions and answers. So I can read at least the first few. At PowerPoint number 4, so the first one I dealt with already. The question was that what I showed on the load combination I showed on the slide did not match BNBC load combination. And my answer is I copied it myself from BNBC. So there should not be any discrepancy. If there is, it is inadvertent. Is there any design difference between floor design and roof design? Is BNBC 2020 differentiate floor element from roof element from loading point of view only? That's pretty much the case. The loading on the roof is different. If a concrete slab is your roof, then I do not see what the difference would be. Obviously, waterproofing is going to be very, very important for the roof slab, not for the floor slab. But as far as structural design goes, I do not know of any difference. With wooden trusses and something as part of the floor system, again, the loading arrangement, there are some things that may have to be done differently. But you are right. It is the loading part that is different, not so much the structural design. At least I cannot think of significant differences in structural design. Is there any limitation of overturning moment according to BNBC 2020? Is there any limit or safety factor between induced moment and resisting moment which we should maintain? Overturning moment, I do not believe. I will check that again, and next week I will specifically mention overturning, because in earthquake situations that is very important. But the second part of your question, you are talking about some kind of an overall stability check. We typically like to have a factor of safety between the the actual overturning moment and the writing, the moment that resists overturning, which should be typically due to dead load, permanent dead load. That kind of an overall stability check I have not seen in BNBC. Dr. Rakib may know. I will check and find out. I haven't seen it. And the factor we typically try to keep is about 1.5. Again, most codes do not talk about that. This is an overall stability check that we engineers feel comfortable with. And a factor of 1.5 is pretty typical. So the restoring moment, as we call it, divided by the moment that is causing overturning. And the same kind of a check sometimes is done against sliding as well, okay? Not just overturning. Do you please explain how to design a building against self-straining forces, stress reversal and fatigue, as well as flood, storm surge, and tsunami loads? Okay. I definitely cannot tell you now because those are big topics. So starting from the end, design for tsunami loads is now a chapter in ASCE 7, starting with the 2016 edition. That is the first time that ASCE 716 added a tsunami resistant design. I can tell you that it is quite complicated. If you find seismic design to be complicated, tsunami design you will find to be 5 times as complicated. And Maria is trying to bring up the questions. Okay. Yeah. Flood and storm surge BNBC actually has given you quite a bit of information. I have not tried to figure out if it is sufficient or otherwise, but I I suppose because Bangladesh has had so many problems with cyclones and the resulting storm surges, that what BNBC contains is probably adequate and quite sound, but I do not know. Self-straining forces, I did talk about. Designing for self-straining forces, I would say, is rather uncommon. They are very important in precast construction, and what we do is allow movement that will relieve the stresses that would have otherwise built up. The final part, stress reversal and fatigue, I do not know that there is one answer. I do not exactly know where to refer you to, except that in bridges, they tend to be bigger problems than in buildings. So in bridge literature, like ash to specs, I have to do a little bit of looking or asking to tell you what the best source is for information on that. Stress reversal and fatigue. Next question. For global temperature rising in Bangladesh in the winter season, the average temperature is between 20 degrees Celsius, and in the summer season, the average temperature is between 35. So my query is it required to perform temperature effects in Bangladesh in buildings, and how to perform this effect? Yeah, I suspected as much. My sense is both variations. Day to night variation in Bangladesh is not that much. Seasonal variation, if it is only 15 degrees centigrade, I personally do not believe that you need to do anything. Frankly, that will not. That isn't. So you go to the final clause that I showed you, that if you can show that it is not going to be a problem, or it is going to be an insignificant problem, then don't worry about it. So based on those numbers, I would say that you do not have a problem. Why live load in balcony is relatively more than bedroom, according to BNBC 2020? That is a very good question. And the reason is people tend to, balconies are outside. You stand on the balcony, you can see a lot more than out of your bedroom window. And particularly in situations like here in Chicago, baseball is a very popular sport, and the Chicago Cubs are a very popular team. They play in a ballpark called Wrigley Field. The buildings around Wrigley Field all have balconies, and on game day, you would not believe how crowded those balconies become. It's unbelievable whether they sell standing room on those balconies. I don't know how much you see out of the balconies. I don't know, but if you looked at those balconies on a day that Cubs are playing, you will easily see why they have to be designed for heavy live loads, because people accumulate on balconies. What is the definition of concentrated load? Concentrated load is exactly what it says. It is, we used to call them point loads. They're not exactly point loads, but they are loads that are applied over a very small area. Okay? So that's what a concentrated load is. What would be a good example? If you take a a big piece of iron and put it on your floor. It's a concentrated load. It will apply a significant load on your floor over a very small area of the floor. Okay, it's not a point load. Point load is kind of theoretical. It is very unusual, but it is a load applied over a very small area of the floor. Okay, BNBC table 624 minimum roof live load table shows for pitched roof with slope 0 less than 1/3 is 1 kilonewton per square meter distributed load, but at the same time, at the reduction of live load shows minimum can be 0.6 kilonewton per square meter if condition meets. Can live load of 0.6 kilonewton per square meter be used if condition meets? Yeah, of course. The whole idea of reduced live load is that you can use the reduced live load in design. So 1 reduced to 0.6 is quite usual, 40% reduction. You definitely can use it. That's the sole purpose of live load reduction. Can the term independent calculation be elaborated a little bit more? And that is a good question. Independent calculation. So that is calculation that is done by somebody other than the designer. So the designer does his calculations or her calculations. The reviewer should do his or her own calculations. And this has been discussed a lot during the S9 project. My own view is the reviewer should not belong to the same design office as the designer, because then there may not be independence. Okay? At least when I started out, this is not always the case anymore. A designer's calculation was always looked over by somebody more senior at the office. And that's not what we are talking about when we say independent calculation. That should be done by somebody that is independent of the design office. Is there any provision existing in BNBC 2020 to perform live load? I don't understand what the question means. To perform live load. Sorry, I do not know what you are trying to say.
It's not Tata Ghosh, it's not live load, it's fire load.
Oh, perform fire load. I see. So you are talking about fire resistant design, probably.
Yes, I think so. Although not exactly relevant to this webinar.
Yeah, much of the code is devoted to that topic, and we already had those seminars, right, on fire resistance, or are they coming up? I don't remember. Anyway, that question does not belong to the structural part. BNBC 2020 does have provisions for fire resistance of structures, very significant provisions that take up quite a lot of space in the code, and we have seminars on them. Okay. BNBC 624 minimum live, no, that one I did already. Independent calculation, fire load. Okay. Why sometimes we use seismic load and earthquake load? What is the difference? That is a very good question. There is no difference. Seismic load and earthquake load are the same. Okay. Yeah, no difference whatsoever is the answer. El sismo is the Spanish word for earthquake. And I say Spanish, it could be Latin or something, I don't know. The seismic is from el sismo, and earthquake does not really have an adjective. We just say earthquake loads, but they mean exactly the same thing. No difference whatsoever. What is the justification of submitting of FEA model file with design report if design review shall be performed through independent calculation? That is a very good question, but it says design review shall be through independent calculation, does not say it shall be only through independent calculation. I would expect that the reviewer would want to look through your modeling, and I think the way it would work is it is left up to the designer whether he wants to do independent calculation to verify some things. He is not going to redesign the building by himself. That is definitely not the expectation. When I saw that, that would be my interpretation. So no, the submittal is important. The reviewer will look through what you submit, and then if there are questions in his mind about some things, he will probably run independent calculation. What is the combination for temperature load? That is in the design load combinations. You will see the T term if you look at the full design load combinations. So it's all spelled out. Helipad load is live load. Yes. The impact is included in the live load. In the IBC, I don't remember, it was in the load combination, some strange place, and it has been moved to the live load chapter now. The load on the helipad when the helicopter lands is definitely a live load for which the helipad has to be designed. Okay. How to perform uplift effects in structures. BNBC just tell us 0.5 times dead load, but my query is, by using this combination, which member deflection we should check? I am not following this question. How to perform uplift effects in structure. BNBC just tells us 0.5 times dead load.
Is this the seismic uplift? The
I don't
vertical
know.
ground motion?
And I don't know 0.5 dead load either. Where is 0.5 dead load? Anyway, if you would maybe explain a little more clearly. Can we record? I don't know that there is any. Yeah, we actually record these seminars, and our intention is to make the records available at some point in time. I do not know how far. I don't keep track. Pro, maybe you can tell them where things stand.
Well, yes, we still have to decide. I mean, yeah, that is the plan. We are recording everything, but we have not processed the recordings where we can then upload. Every recording needs a little processing, editing at the end. That hasn't happened, and that is pretty much the only thing that is stopping us from. But when we do, you do it on we would upload them on YouTube.
Yeah.
And send you the links somehow.
Now it is well past 9:30. I unfortunately have to, I have another meeting. PCI convention is going on, and the meeting started at 10 our time. It's 10:35 our time here. So I better go on to that meeting. There are probably a lot of questions left, and we again have not come to a satisfactory way of dealing with the questions because there are so many. But we are thinking and trying, believe me. Okay, so tomorrow will be wind. That is a huge topic, and I'm still struggling with the slide set. But anyway, I'll finalize after the other meeting, and we will have a hopefully a good seminar, and hopefully you have enjoyed much of today. So I'll look forward to seeing all of you tomorrow at the WIN seminar. Thank you.